Hello, everyone. Glad to see you all. Okay. There is a session today. I'm going to share my screen. Mhm. Okay, you should see my screen. So please let me know if you can't see my screen. If you do, then that's fine. Also, let me know if you don't hear me, which might be difficult, but okay, right. So we're talking about DC circuits today. So well done on completing assignment 1. The results would be in hopefully next week. We'll give you the results. But yeah, brilliant. DC circuits. Well, I mean, yes, sure. Copy the Miro link. Lovely. You know DC circuits, like that circuits. You know how they work. If you don't, please do try this out. So I really like this. So you just take a battery, a light bulb, and a wire, and you connect. And you can see those electrons inside the wire. So these are the free electrons. The structure of a metal has free electrons inside, also known known as delocalized electrons. The follow along program. Yes, you will. Okay, right. I'll show you how to join the follow along program. So year 10 follow along. Here's a link to join the follow along program. So don't everyone click it. Just only if you want to join follow along program. Follow along. Okay, so this is a simple circuit. So electrons go around the circuit. The battery provides energy to those electrons. And then these electrons go to the lamp and the energy lamp transfers that energy into light and heat. And then the electrons go back to the battery to get some more. What is follow along? Follow along program is a program for those people who either don't get in to the main program, or people who don't want to spend 4 to 5 hours a week doing the main program. So this is like a light version of COMPOS. Okay, follow along. I explained it in the webinar 02, So please watch webinar 02 if you don't know what the follow-along program is. Okay, so it's a simple circuit. We know that if we break the circuit, it stops working, and yeah. Well, let's look at this diagram. So one of our students, actually, a COMPOS student, has drawn this for us, and we're going to use it. So this is a water circuit. So water flows. This is a tap. Water flows, and webinars are for everyone, full stop. Anyone who wants to watch the webinars, they're for webinars. The follow along only for those who either don't want to main the joint program, or when you don't get in, we will send you the link anyway. Okay, so water flows in a circuit. There's a pump that pumps the water up to a higher level. We say to a higher potential energy. Remember, gravitational potential energy is mass mgh, where h is the height. So if you change the height, you change the potential of the water. Potential of the water increases. That's why we say potential difference. So this is known. This is potential difference. Potential difference. So this is what the battery does. The battery puts the electrons onto a higher shelf, onto a higher potential. Okay? And as the electrons fall down from that shelf, they can do useful work as the electrons. So the battery raises the potential. So let's say the potential here is 0 volts. The potential here is 9 volts. So this is a 9-volt battery. That's what it does. So for example, we can say that this water level is 0 meters above the ground, and this is 9 meters above the ground. So this is similar to that. Then the current, the charge flows, and then the charge flows through that resistor. So here it still has 9 volts. The potential is 9 volts, and as it passes through the resistor, it loses back to 0 volts, and then comes back to the, well, if this is closed, of course, back to the battery to raise the potential again, go to a higher shelf, and for then just to fall down from the top shelf down and do some useful work on the way down. So electrons do useful work as they lose potential. When we say potential, it's very similar to potential energy. You don't need to know what potential is for GCSE, but potential is the energy divided by, well, you do need to know the potential difference, is the energy divided by charge. So basically what this means is that the potential is proportional to potential energy. This is potential energy, of course. Electrical potential energy, or gravitational potential energy in this case. Does this explanation make sense to you? Do you see how the electric circuit is very similar to a water circuit, and how the change in height of the water is equivalent to changing the potential of the water? On a scale of 0 to 10, please give me a number. 10, I understand fully. 0, I have no idea what you're talking about. Okay. Okay. let's go back to this. So the battery pushes electrons. The battery supplies electrons with energy. The electrons carry this energy into the lamp to do some useful work. Okay. Battery takes, so these electrons come, they are low energy. And the battery gives them energy. Battery gives them energy. And now you have high energy. High energy. Now these electrons, they travel, they go to the lamp. There's still high energy here. And this energy is used up. Well, it's not used up, it's transferred as light and heat. And then the electrons have lost their energy and they have low energy. And they go back to the battery to get some more. Do you understand this diagram on a scale of 0 to 10, please? Especially those who scored below 6 in the previous one. 6 or below. Okay, that's good. So this is what I'm trying to say. The water, so this picture here. So the pump, this has low energy. This water has low energy because it's low down. The pump pushes the water up, and now the water has high energy. But rather than saying energy, we use the word potential, which is a very similar thing. And then this water has high energy, and it's ready to do some useful work on the way down. So for example, there could be a wheel, and the water spins that wheel on the way down. So water does work. Just the same way electrons do work. Electrons do work as they go through the lamp. Water does work. So the energy, when we're talking about energy, is, we say, high potential. So high potential. Potential is measured in volts. So for example, if we say that this is here, we have we have 0 volts here, 0 volts, 0 volts. In let's say the battery is in a 9-volt battery, that means the battery supplies 9 volts. So 9 volts, 9 volts, 9 volts, 9 volts. So the battery does the equivalent of a pump, pushing the electrons high above, and then the electrons do work on the way to a lower potential. Okay, how about now? Do you understand how these two are very, very similar on a scale of 0 to 10? Another vote, please. Okay. Well, still progress. Couldn't do 100%, but still progress. Okay, good. So when we say high potential, we basically mean electrons have high energy. And this is what potential difference is. Potential difference is the difference in potential. So for example, if we were to take 2 lamps and we measure the potential. So the voltmeter measures the potential difference, measures the difference in energy. So it's a 9-volt battery. That means that the electrons gain 9 joules for every coulomb of charge. Now on this lamp, they lose 4.5. And on this lamp, they also lose 4.5. This is equivalent to this diagram. So the battery takes the water from 0 meters to 9 meters above the ground. The first ramp, the first resistor, takes the water from 9 meters to 4.5 meters. And the second ramps, the second resistor, takes the water from 4.5 meters to 0 meters again. So the electrons here have 0 volts. Okay, not electrons, the charges here have 0 volts of energy, 0 volts of potential. Then the potential goes up to 9 volts of potential, plus 9, plus 9, plus 9, plus 9. And then when you go down, it goes to plus 4.5. And then from 4.5 to back to 0 volts. 0 volts, 0 volts. So when you connect a voltmeter, what you are measuring is you're measuring the potential difference, the difference in potential. So for example, here, the voltmeter will register what? What would the voltmeter register? Potential difference. Yes, 4.5 volts. Potential difference, which is 4.5 volts. Okay. A volt, 1 volt is 1 joule per coulomb. 1 coulomb is 1 joule per every coulomb. So volt is equivalent to energy, is just energy per charge. Okay, so that is how voltmeters work. So what do you think would happen if I press? Oh, there's no pause. If I connect a voltmeter here and here, what do you think would happen when I flip the switch? What would the voltmeter show? Yeah, look, it shows 0 volts because we're not losing any energy. The potential difference is 0 because it is 0 volts here and 0 volts here. And similarly, if I connect a voltmeter here, because this is 9 and 9 minus 9 is 0. The potential difference is 0. Okay, so hopefully I've managed to get the idea across to you. Now let's talk about current. So just some definitions. So the voltage is the potential difference. It's the energy supplied or transferred per unit charge. Okay, so voltage is the energy supplied or transferred per unit charge. So let's say it's 1 volt is 1 joule per 1 coulomb. A coulomb is a unit of charge. Can somebody please share the Miro link in the chat? Now, current is the how many coulombs flow per 1 second. Thank you. It's how much charge how much charge per unit time. So 1 ampere is 1 coulomb per 1 second. That's also important. Okay. So what does that mean? It just, if we put an ammeter here, this is called a non-contact ammeter. These exist. You put them around the wire like this. Put them around the wire, and they measure the magnetic field produced by the current, and then thus they can tell you how much current there is. The current in the wire is 0.45 amps. That means 0.45 so this means 0.45 coulombs per second. A coulomb is just well, it's a lot of electrons. One coulomb is a bag of electrons. It's just a chunk of electrons. So how many electrons? So imagine a bag of electrons, and 6.25 times 10 to the 18 electrons. That's how much a bag of electrons is. So it's 6.25 and 16 zeros. So lots of electrons. That is what 1 coulomb is. All right. Now let's look at a series and a parallel circuit. So this is a series circuit, and you can see that the current at any point is the same. The current is the amount of water per second. So current is the amount of water per second. So if you have, I don't know, 3 kilograms of water per second, here you have 3 kilograms of water per second. Here you have 3 kilograms per second, kilograms of water per second here. So anywhere in a series circuit, series circuit, current is the same at any point. The voltage. Well, if you look at the potential difference, so the voltage on the battery, V battery, V on the first resistor and V on the second resistor, the voltage. So the potential difference on the battery must equal the potential difference on the first resistor plus the potential on the second resistor. That's the rule for voltage. In a series circuit, the voltage on the battery splits between components. Okay. Right, so here you have the battery is 9 volts. This is 4.5, and this is 4.5. They don't have to split equally, of course, and you probably know that. So if we change this lamp to something else, so we can see that this is 1.7 and this is 7.3. Together they make 9, but they're not equal. So this is 7.3, this is 1.7. In a parallel circuit, so you can see that the water raises, so the potential raises, but then For every resistor, the potential difference is the same because the difference in water level, this is 9 meters and 0 meters. So in a series, in a voltage is the same for each component. So if this is 9 volts, then this is 9 volts, and this is 9 volts. Current splits between components. And we can see that here is a narrow tube, and here is a wider tube. That means there's more water flowing through this component. So let's say there is the current here is 7 kilograms per second. We could have 5 kilograms per second here and 2 kilograms per second here. So the flow rate would be different because the water, and then the flows would join together. There's 2 and 5, and they go back to 7 kilograms per second. Similar here, if you have a current flowing from the battery, let's say 7 amps. 7 amps. This is 2 amps, and this is 5 amps. So the current splits and then rejoins back to make 7 amps. 5 amps, 2 amps. Okay. So to summarize, in a series circuit, the current is the same everywhere. Current, same everywhere. Voltage splits between components. Okay, so first, current. We call this rule current rule. Let's call it 1, 2, and let's say series 1, series 2. They don't really have these names, but parallel 1, parallel 2. Series rule 1, current is the same everywhere. Series rule 2, voltage splits between components. Parallel 1, voltage is the same for each component, and P2, current splits between components. How well do you understand these 4 rules? S1, S2, P1, P4. On a scale of 0 to 10 again, please. Okay. The rules you should have studied in school. And hopefully now you understand them better with this water circuit analogy. Of course, it's not a perfect analogy. So, for instance, a current can't go anywhere from the circuit, but water can pour out of the circuit. But anyways, resistance. Now, it's kind of jumping into resistance. Resistance is simply voltage divided by current. This is known as the Ohm's law. Ohm's law. Resistance is voltage divided by current, and that is the definition of resistance. So, what is resistance? If somebody asks you what is resistance, you have to say resistance is voltage divided by current. Well, let's have a look. For example, if we take the current through this lamp and the voltage, so we can see that voltage divided by current. Well, let's do that. So resistance R1, let's call it R1, is voltage divided by current, V1 divided by current, which is 7.3 divided by 0.17, and that is 7.3 divided by 0.17, which is 43 ohm. And resistance 2 is the voltage, and remember the voltage was 1.7 divided by 0.17 and the current is the same, 0.17. V2 is 1.7 divided by 0.17, so it has to be 10 ohms. Let's check. We click on this lamp and you see that the resistance is indeed 10 ohms. And we click on this lamp and the resistance is indeed 43 ohms. Okay, they're quite neat. This is what resistance is. Now, if you have two resistors in parallel, then you have to add their resistances. So you have R1 and you have R2. The total resistance is R1 plus R2. Unfortunately, I don't have enough time to prove that today. So do something that you never should. Believe me. Okay, not that you shouldn't believe me, it's just like you have to develop your own critical thinking. Whenever somebody tells you that this is true, do double check for yourself. Okay, do double check at least with your own understanding of the universe. Okay. And otherwise, if you don't check, then you have things like, 5G networks will control you through vaccination or things like that. So you get silly ideas coming from people who don't understand science. Right, so the total resistance. So if you have a 5 ohm and a 10 ohm resistor, the total resistance is going to be, no, please don't do that. Okay. The total resistance is just going to be adding the two. Let's see if that actually works. So if we have 43 and 10, so let's do the total. So we measure the voltage across the two, and it's going to be 9 volts. 9 volts and divided by 0.17. Let's see if that actually works. So resistance of the two lamps, because now we're measuring the voltage across the two lamps. Resistance is the voltage divided by the current, which is 9 volts divided by 0.17 amps, which gives you 9 divided by 0.17, 53 ohms. Ta-da! Yes, this was 43 and this was 10, so in total that's 53. Makes sense. It works. It adds up. If you have resistors, oh, sorry, that is resistors in series, of course. Series. Now resistors in parallel. Well, if you have R1, then you have R2, then R total is equal to, 1 over R total is going to be 1 over R1 plus 1 over R2. All right, let's see if that actually works as well. So I'm going to clear everything. Okay, battery, resistor. Let's make this 20. And this is 10. And we're going to connect it. Just for simplicity, I'm going to switch that to 60 volts. All right, and the voltmeter is obviously 60. 60 here and 60 here, because it's a parallel circuit. Okay. With the ammeter, we have 3 amps here and 6 amps here. So 3 amps here, 6 amps here. Okay, so let's do that. Test. So what we're trying to test, so we find R1. R1 is going to be 60 volts, is voltage divided by current. So that's 60 volts divided by the current, which was 3, and that makes 20 ohms. R2 is voltage divided by current, is R2 I2, V2 V1 I1, V1 I1, V2 O2. So it's 60 divided by I2, which is 6 amps. 60 volts, amps. And that is 10 ohms. And our total is going to be the voltage total, which is still 60, divided by the total current. And this was 3 amps and that was 6 amps. So 9 amps, the total. So there's going to be 60 volts divided by 9 amps, which is 60 divided by 20, 20 divided by 3, which should be 6.7 ohms approximately. 6.7 ohms. Let's check if that actually works. 1 over 20 plus 1 over 10. There, so you multiply this by 2, that's 3 over 20. And that's 1 over R total. Then from here, R total is 20 over 3 ohms, which is 6.7 ohms. Ta-da, it works. Works. Okay, so we have this formula. We have this formula for resistors in series, resistors in parallel. The interesting thing is the total resistance in series will always be bigger. Is always bigger, and resistors in parallel always smaller. Total always bigger, and then total always smaller. Okay, then total always bigger than the biggest resistor, of course, and then the total always smaller than the smallest resistance. Good. So these are the rules. So these are easy combinations. So if you have a 6 and a 3, that makes how much? Oh, 9 ohm. Easy. Oh, this one is not that easy. You have a 1 and a 2, and there's a 4 in parallel with a 4. So 1 and a 2 make 3. So what do we say, well, this could be just one resistor with the it's a 3 ohm resistor. So together they make one 3 ohm resistor. And now we have 3 and 4 in parallel. And to find that, you do 1 over R total. That's equals to 1 over 3 plus 1 and 4, which is 4 plus 3 over 12, which is 7/12. So R total is 12 over 7 ohm, which is, well, approximately 1.1 1.71 ohm. You can see that the total is 1.7 ohms, even if you have 1, a 2, and a 4, and together they make 1.7. All right. Do you understand this problem? How to do this? Would you be able to solve this problem by yourself on a scale of 0 to 10, please? Okay. For this one, easy. So we have two resistors in parallel. So 1 over R total is 1 over 6 plus 1 over 3. So you add the two fractions, and that's, you need to find the common denominator. The common denominator is 6. So 1 plus 2, that's 3 over 6, which is 1/2. But then this is 1 over R total. If you want R total over 1, so you flip both sides. So R total over 1, you flip this over, or bam, flip, and you get 2 over 1, and that means R total is 2 ohms. Okay, so a little bit of maths manipulation here, but total is 2 ohms. So these two resistors can be replaced with a 2 ohm resistor. 2 ohm resistor. That's it. Very neat. Very nice. Why would you use two resistors instead of one? Oh, different reasons. If one stops working, the other one still works. That's one reason. Then resistors can overheat sometimes. So splitting between two resistors is making sure that you are not overheating the system. Okay. Overheating the resistors. Now this one, sorry, I made a mess here, but this is R1, and this is R3, and this is R2. So basically what I want is to do the problem, but with just algebraic manipulation. So what is the total? So first we find the combination of the R1 and R2. So let's call this combination RC, R combination. 1 over RC. So this is going to be get a bit math algebraic. It's 1 over R1 plus 1 over R2. As a matter of fact, the common denominator is R1, R2, and this is R1 plus R2. Yeah, if you add the two fractions. So here you can RC is R1, R2, so you flip them over, bing, over R1 plus R2. And actually, this is a valid formula for two resistors in parallel. For two resistors, you can use this formula. R total is R1, R2 divided by R1 plus R2. This is just a rearrangement of the above formula. So if you rearrange this, you won't get this. But it doesn't work for 3 resistors. So well, this formula works for any number of resistors, but the bottom formula only works for 2. But it's still handy. And now we have the R3 combination. So R total is going to be RC plus R3, which is R1, R2, R1 plus R2 plus R3. I would never consider actually simplifying this into a single fraction, but this can be done. Yeah, so you would multiply this by R1 plus R2. So you would get R1, R2 plus R1, R3 plus R2, R3 divided by R1 plus R2. I don't see why anyone would do this, but you can do it. Just because you can doesn't mean you don't need to do it. Now, it is very crucial that you understand this bit, because the next problem, we would be doing that, but harder. So on a scale of 0 to 10, do you understand how I got this answer? Problem D, on a scale of 0 to 10, please. It's pure algebraic manipulation. There's nothing else. Like, it's not even physics. It's just algebra. Good. Okay, so that's not bad. Okay. And so the infinite resistor network. What on earth can we do here? So I've modified the question so it's not the same as the one in the assignment, but still it will help you a lot. So basically it's an infinite chain of resistors. And the question is, if you connect that to a circuit, what is the resistance? That's what we're trying to answer. So if the current flows here, how much resistance does it experience going from A through the resistors and to B? And the idea is that there's an infinite number of these resistors. Well, that's if we assume that the resistance is finite, we can say, well, the whole thing can be replaced with a single resistor at A and B. And if we, let's call it RT. So this whole combination is an infinite combination, of course, because there's infinitely many resistors, can be replaced with a single resistor, with the resistance RT. And our task is to find RT. Okay? I hope everyone's on board. That's what it means to find the total resistance. Is if we were to replace the whole thing with just one, what would that one be? Okay, that's step one of doing this problem. Step two in doing this problem is realizing that the chain is actually infinite. And adding another pair of resistors on the left, you will now have infinity plus 1 resistors, which means it's just still infinity. So adding another 6R here and another 4R here, you know what? I don't want to do 4R. I just want to do 4 ohm. 6 ohm, 6 ohm, 6 ohm. 6 ohm, 6 ohm, 6 ohm, 6 ohm. Adding another link, another pair of resistors on the left does not change the total resistance because it's just another pair in an infinite chain. Adding another pair won't change the total resistance. That means that this combination is exactly the same as this combination. RT 6 ohm, 4 ohm, 4 ohm. So let's find the total resistance of this using the stuff we did before. So for this pair, let's call it RC again, our combination. RC, 1 over RC is 1 over 6 plus 1 over RT. 1 over RC is 6 RT divided by RT plus 6. RC is 6 RT divided by RT plus 6. Okay, that's the resistance of this, and plus 4. So the whole thing is 4 plus 6 RT over RT plus 6. But since this whole combination is equivalent to this one, the total resistance of this combination has to be RT. Okay. Have I lost someone here? I hope not. So first step, you realize that the whole thing can be replaced with just RT. Then you realize that adding another pair on the left won't change anything because it's an infinite chain. And that means that this combination is equivalent to this combination. So we find the total resistance of this combination, and it's this, 4 plus 6 RT over RT plus 6. And the resistance of this is just RT. And we make them equal. And now we have an equation, and we need to solve for RT. Solve for RT. And that becomes 4RT plus 24 plus 6RT equals RT squared plus 6RT. So what I did is I multiplied the whole thing by RT plus 6. So 4 times that's this bit. You know what? Let's not skip a step. Skip steps. I multiply by this. So I get 4 RT plus 6 plus 6 RT equals RT, open bracket, RT plus 6. And I open the brackets and I get a quadratic equation. And you are good with quadratic equations because you've done a whole assignment on them. Minus 4 RT minus 24 equals 0. I'm going to go with a fancy completing the square here. So RT minus 2 squared minus 28 equals 0. Is it? Minus 4 plus 4 minus 4 minus 28. Yes, so RT is 2 plus or minus square root of 28. And of course, resistance cannot be negative. Therefore, RT is 2 plus root 28 which is approximately what? Well, root 28. That's 2 root 7. 2 plus 2 root 7. And root 7 is more than 2, less than 3. So it's about 2.5. So it's approximately 7 ohms. My calculator, 2 plus 2 root 7. 7.3. 7.3 ohms. Quite close. 7.3 ohms. So yeah, that's how you solve an infinite chain. To solve an infinite chain, all you need to realize is just if you add another one on the left, that doesn't change anything. Okay. You have 3 100 ohm resistors. Draw all possible combinations and find their resistances. Find the power output when connected to a 240 volt outlet. Well, the power can be written as current times voltage. But also power, because current can be written as voltage over resistance, we can write power is V squared over R. Also, P can be written because voltage is current times resistance. Power can be written as I squared R. So there are 3 formulas for electric power. And all 3 are useful. The first one is useful when you don't know R. The second formula is useful when you don't know I. And the third formula is useful when you don't know V. Okay. You have 300 ohm resistors. Draw all possible combinations and their resistances. Okay, so first, well, the first is like this, easy. 3 resistors. So that's 100, 100, and 100. P is power. Is power. Okay. Power is how much energy per second. Power is measured in watts. Wendy, we use, well, it's not confusing because you don't normally see pressure and power in the same question. That's why we don't see a problem of using them. In the rare case that we do, we just redefine them. We say power, very, very commonly, power, we use N for power. Yes, but when we did pressure and when we do pressure, we will learn that pressure arises because particles change momentum. A particle with momentum P1 hits the wall and bounces back with momentum P2. So the pressure is the number of particles times the change in momentum, which is also P. Okay? So lowercase p for momentum. That's why we prefer sometimes using capital P for pressure rather than lower p for pressure, because we also have momentum is mv, and momentum and pressure are linked. That's why we tend not to use the lowercase, but it really doesn't matter. It's not incorrect. It's just it's a matter of definitions. because momentum and power often go together. Momentum and power often go together in the same equation. Pressure and momentum often go together. Pressure and power very rarely go together. So, yeah, both are correct. Look, honestly, for pressure, I always use lowercase p. Okay, so it's just closer to me. In the exam, you can always say, I don't know. They say give the equation for Ohm's law, and you know that Ohm's law is voltage equals resistance is voltage over current, and well, actually it's current equals voltage over resistance. You could always write it as like A equals W over X, where A is resistance. I don't advise you doing this, but W is voltage, and X is current. This would be bizarre, but it would be correct. I mean, even in GCSE, that you would still score full marks. But yeah, I'll delete that because please don't do that. So the first combination, 100, 100, and 100. And so we know that the total resistance, let's call it R1, is 300 ohms. Then the power, we know that it is connected to a 200 volts outlet. So that means that the voltage is 240 volts. Which formula would we use? The first, the second, or the third formula to find the power? The second, of course. We use the second because we don't know I. We do 240 squared divided by 300, which would give us something like 180-ish, 240 squared, 192 watts. That's the power output of this. What does it mean? What does this number mean? This is important to understand. The resistors will produce or transfer. Resistors will transfer 192 joules of thermal energy, of heat, every second. So they will heat up. Resistors heat up. That's what they do. That's how your electric heater at home works. You switch it on, there's a resistor inside, it heats up, and it gives you heat. 192 watts is not a lot, honestly. It's 192 watts can barely heat one room. But yeah, a typical electric heaters start with 500 watts. Now the second combination. Well, the second combination is also an easy one. It's 3 resistors in parallel. Parallel. And because this is 100, 100, and 100 ohms, that means 1 over R total is 1 over 100 plus 1 over 100 plus 1 over 100, which makes it 3 over 100. So R total is 33.3 ohms. The total resistance is always smaller with parallel resistors. So the power output is going to be 240 squared divided by 33.3. which gives us 240 squared times 3 divided by 100. 1,728 watts. That means 3 resistors in parallel would produce 1,728 joules of heat every second. So these would be much hotter. This system would give you much more energy. Okay, 3. Well, you can connect them like this. 1 and 2. So that's going to be 100 and 100. So total is 50. 50 and 100. So that's 50 because 2 resistors in parallel halve the resistance. So our total is 150 ohms. And the power R3, sorry, R3, no, that's R2. And the power 3 is 240 squared divided by 150. 240 squared divided by 150. 384 watts. And for the fourth possible combination of 3 resistors is this. 2 parallel. Like this. 240 volts. This is 100, 100, and 100. So 100 and 100, that's 200. So that's 200 in total, 200 and 100. So R4, 1 over R4, that's 1 over 100 plus 1 over 200, which is 3 over 200. So R4 is 200 divided by 3, which is 67.7 ohms. And the power output is 240 squared divided by 67.7 ohms, which is going to be 1728 divided by 2. It's going to be 864 watts. So as you can see, the parallel combination is the most powerful one, which gives you the most heat. And then the series combination gives you the lowest power, so the lowest amount of heat. And then you have 2 intermediate ones. So this one, the 384, and the fourth. Oh yeah, 66.7, sorry. Thank you. 66.7. I cheated. I didn't actually calculate it. So it should be 164. So yeah, as I said, don't believe what people say, especially me. Or no, just not especially. Just double check the information that you receive. That's what being a good scientist is all about. Kirchhoff's laws. Well, these are examples from the assignment. So I really hope you would be able to follow with the Kirchhoff's laws. But let's just talk about Kirchhoff's laws in general, and if we have time, we'll get to the examples. So there are 2 Kirchhoff's laws. Kirchhoff's law 1, current at a node total. The sum of the currents at a node is 0. What does that mean? Well, that means if you have a node is a point where several wires come in. So for example, if your current I1, I2, I3, and I4, you have two currents flowing in, two currents flowing out. The total current flowing in, so I1 plus I4, minus the currents flowing out, minus I3, is 0. Or you can say I1 plus I4 is equal to I3 plus I2. Currents flowing in equals currents flowing out, I3. Okay, so currents going in equal current going out. Easy, very straightforward. And that's the easy Kirchhoff's law, also known as Kirchhoff's law 1, the current law. The second law is much trickier, but hopefully you'll manage. The sum of potential drops and rises is 0 around any closed loop. Well, what does that even mean? The sum of potential drops and rises around any closed loop is 0. Let's go back to this diagram here. Can I make a copy of it? Oh, it is from the assignment, so I'm just going to take from the assignment. I'm more interested in the examples of Kirchhoff's second law because Kirchhoff's first law is easy. Okay, so let's say for this example, here the water is at 0 meters, and here the water is at 9 meters. Here the water is at 4.5 meters, 9 meters, and 0 meters. So as the water goes round the circuit, it goes up plus 9 meters. Then it goes down 4.5 meters. And then it goes down again, down 4.5 meters. So that's a rise, and that's a drop. Rise, and this is a drop. And this is a drop. The sum of drops and rises is 0. Let's see. Kirchhoff's second law says the sum of drops and rises equals 0. So first it rises by plus 9 meters, then drops down by 4.5 meters, and then drops down minus 4.5 meters. And then you come back to the where you started. So in a closed loop, and that's equal to 0. Does this make sense? The sum of drops and rises in the water level is 0 in any closed loop. Do you understand on a scale of 0 to 10, please? Okay. The same works for a circuit. Okay. Two, 237. Yeah, of course it works on a parallel. So this is a closed loop. So the battery rises the potential. So it's a rise, goes up to plus 9 volts. Now we measure potential in volts now, not meters. Or meters is the height, of course. Plus 9. This resistor drops the potential by minus 2 volts. This resistor drops the potential by minus 3 volts. And this resistor drops the potential by minus 7 volts. Because this is a 9 volt, this is a 2 volts, this is a 3 volts, and this is a 7 volts. Well, we know that it drops because we lose energy in the resistor. We gain energy in the battery, we lose energy in the resistor. And now going around the loop, so let's say we're going around this loop this way. So first we encounter the battery, so plus 9 volts, minus 2 volts, minus 3 volts, minus 7 volts equals 0. So that's Kirchhoff's second law. So it works. So if I ask you, what is the voltage here? V2 is question mark. You say it's 3. It has to be 3. Okay. So let's see how it works with a parallel circuit. So let's take the parallel circuit diagram. Okay, so here you actually have 3 loops. So let's look at loop 1. This is loop 1. Loop 1. So we're going around this loop this way. So first we encounter the pump that is plus 9 meters, and then you lose minus 9 meters. So plus 9 meters, minus 9 meters. So that's 0. Let's look at loop 2. Loop 2. Loop 2. Now the battery, again, is plus 9 meters. And then you lose minus 9 meters as you go down. So minus 9 meters. The sum of raises and drops is 0. Now loop 3 is the trickiest of all because it's, what color should I use? Okay, purple. So it's this one. You're going around the loop. So let's say you're going around the loop this way. So here, as you go down, you lose minus 9. So loop 3. You go down, you lose minus 9. So minus 9 meters. But now you're going against the flow. The flow is backwards, but you're going up the hill. You're going up the hill, so it's plus 9 meters. You're going against the flow of the water. So plus 9 meters, and that's 0. Okay, so same here. Because the current is flowing this way, the battery, 9 volts. This is 9 volts and 9 volts. So in the first loop, loop 1. You're gaining energy in the battery, so plus 9 in the battery, minus 9 in the resistor, and that total is 0. If you take the green loop, loop 2, you get plus 9 volts in the battery, minus 9 volts in the resistor, plus 9 volts minus 9 volts is 0. And finally, loop 3, you lose 9, so minus 9 volts here, but plus 9 volts here because you're again going against the flow of current. So minus 9 volts plus 9 volts is 0. So you're going against the flow. Same here. In this, against the flow. Right? Oh, the battery. Yes, sorry. The battery is 12 volts. Apologies. Silly. This is the essence of the Kirchhoff's laws. Do you think you understand Kirchhoff's second law about the loop on a scale of 0 to 10, please? 9.9. Good. All right, so let's have a look at this. Kirchhoff's first law is easy, right? Because this is a node. You have 1 amp flowing in, 2 amp flowing in, and 3 amps flowing out. That makes sense. So for node A, Kirchhoff's one for node A, you have plus 1 amp, plus 2 amps, minus 3 amps, that's 0. That works. For node B, you have 3 amps flowing in, so plus 3 amps. Then you have 1 amp flowing out and 2 amps flowing out, so minus 1 amp minus 2 amps equals 0. So that works. That's the easy part. Now, you can also do for node E if you wish. I mean, honestly, this is 2 amps going in and 2 amps going out. So that's not a problem. A node doesn't have to have more than 2 wires, right? So a node can have just 2. And even 1, yeah, if you have like this. Unless you have a capacitor. All right, never mind. That's yeah, with 1 it also works. Kirchhoff's second law. Well, here you need to take loops. So let's take this loop over here. And we go clockwise. We go in this direction. So loop D, A, B, C. So the battery raises the potential. So you go from low to high potential. You go from minus to plus, low to high. So you go plus 12 volts in the battery. Then you go bum, 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 you encounter the resistor. The current is in this way. That means that the potential drops. You're losing energy as you go through the resistor. You're not going against the flow, you're going with the flow, so you're losing energy. So minus 3 volts in the resistor. And then you have another resistor, you once again lose minus 9, minus 3, minus 9, so that makes minus 9 volts, and that's 0. So that checks out. Let's take another loop. Let's take loop AFE, ABEF. So we draw this loop. Loop A, B, E, F. We have plus 12, minus 11, minus 1 volt, which is 0, of course, checks out. And the most interesting one, purple, is the outside loop. Now, here at places you will go with the flow and somewhere you will go against the flow. So it doesn't matter which way you go. Let's go clockwise. So loop D, A, F, E, C. D, F, E, C. We don't need A. D, F, E, C. Let's have a look what's going on in here. So we have DA. So we have blah, 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 blah. Now here we're going against the flow of current. The current is flowing left and we are moving around the loop clockwise. So it's going to be plus 1 volt, plus 1 volt. Once again, we're going against the flow of current here. So rather than losing energy, we're actually gaining energy because we're going uphill. So plus 11 volts. Now moving on, so the resistor. In the resistor, we're going with the flow of current. The current is that way. So we're losing 3 volts, and then we're losing 9. And once again, that brings us back to 0. This is how it works. And this is how you use it. This is how you use it. So you have 2 batteries. You have 2 resistors. Well, yeah, it's example 7, but I think it's worth doing it. We need to choose the direction for currents. So let's say the current flows that way, and we label this I1, I1, oh, I1. And then here the current is likely to go this way. It doesn't have to be this way. If, for example, we solve and we find that I2 is negative, that means our guess was incorrect. I'm guessing that this is going to be this way. And the bottom current, rather than calling it I3, I'm immediately going to use Kirchhoff's first law. What would the current be here in terms of I1 and I2? I1 plus I2 indeed. I1 plus I2. Because if the current is I1, this is I2, this is I1 plus I2. We're talking about current. All right. Now let's label the voltages. So this is the battery 1. Yeah, that's obvious. So battery 1. This is battery 2. We call this V, let's call this V1. And this call this V2. And this call V3. We know that V1 is current times resistance, which is I1 multiplied by R1, which is 10, which is 10 I1. So the voltage 1 is 10 I1. V2 is going to be 15 I2 in a similar manner. Yes. And V3 is going to be 20 multiplied by I1 plus I3. Now let's go around the circuit. Let's go around the circuit. Let's take loop 1. We don't need to take all 3 loops. This loop 1. So loop 1. So it's going to be plus 5 volts. That's the voltage here. Minus 10 I1. Minus V1, the voltage here. Minus V3, the voltage here. And that must equal to 0. Then we take loop 2. Let's say this loop. Loop 2. So this is voltage on the battery, so it's plus 10 volts. Minus V2. And then minus V3. And that's also equal to 0. So from here, we have 3 unknowns. So we can't solve the 2 equations. And if we do a third equation, that won't help, actually, as a matter of fact. But what we can do is remember this, that V1 is 10 I1, this is 15 I2, and this is this, and substitute that in. So we have 5 minus V1, which is 10 I1, V3, so minus 20 I1 plus I3, that's equal to 0. And then we have 10 minus V2, which is 15 I2, and then minus 20 I1 plus I3 equals 0. Now all I need to do is to solve I1, I2, that's silly, I1, I2. This simultaneous equation, so you have 2 unknowns, 2 equations, 2 unknowns. So 5 minus 10 I1. Minus 20 I1 minus 20 I2 equals 0. 10 minus 15 I2 minus 20 I1 minus 20 I2 equals 0. And then you simplify that. So 30 I1 plus 20 I2 equals 5. And then you have 20 I1 plus 35 I2 equals 10. Whichever way you like. I like elimination, so I multiply this by 2, multiply this by minus 3, and I get 60 I1 plus 40 I2 equals 10, and I get minus 60 I1 minus 105 I2 equals minus 30. Oh, that's an arrow. It's an arrow, which means hence. Hence. Or it follows that. Or yeah. And then you simplify this, so that's you add them together, so that's minus 65 minus 65 equals minus 20 I2 equals 20 over 65 0.31 amps. And then in a similar fashion, you can find I1, which gives you something else. But yeah, that's in the assignment. You can check that. I really hope that this makes sense. Like, I mean, it just approximately here, this is where physics ends. So everything to this point is physics. Everything to the right of that, that's just maths, just solving simultaneous equations. So very straightforward. Okay, I hope this helps. Please watch my other webinars. I have done a few on this topic. And yeah, enjoy completing this assignment. It's due in a month, so you have more than a month to finish it. Okay, enjoy.